Okay, so let's talk about radiocarbon dating. Okay, so let's do an example of involving radiocarbon dating, and we're going to talk about carbon-14. Okay, so one of the most common applications of an exponential decay model is carbon dating. Carbon-14 decays at a regular and consistent exponential rate. Okay, so what do we mean by decay? It emits radioactive particles. Okay. Therefore, if we know how much carbon was originally present in an object and how much carbon remains, we can determine the age of the object. The half-life of carbon-14 is approximately 5,730 years, meaning that it takes that amount of time for half of the carbon to decay. So now, let's see here. If we have 100 grams of carbon-14, today, how much is left in 50 years? Okay, so let's figure this out. Well, we know the halving time is 5730. We also know that the formula is the natural log of 2 over K, right? So we need to find K. So that means K is going to equal the natural log of 2 over 5730. Okay, so now, what's the formula? The formula is equal to y equals y naught e to the negative kt. So we want to know how much is going to be left after 50 years. So we know we have 100 grams, and we know that K is equal to the natural log of 2 over 5730, and T is 50. So all we have to do is stick this into our calculator. And so if you stick that in your calculator, you get approximately 99.4. 99.4 years. So almost 100 years it'll take for the 100, oh, I'm sorry, wrong question. We will have approximately 99.4 grams of carbon-14 left. Okay, so the next question it asks is, if an artifact that originally contained 100 grams of carbon now contains 10 grams of carbon, how old is it? Okay, so in this case here, we're looking for the amount of time that went by. So we know that it has 10 grams, right? So we're doing y equals y naught e to the negative kt. So we know there's 10 grams left. There was originally 100 grams. And we know K is a negative natural log of 2 over 5730, and T. So we're looking for T. So now we're going to solve for T. So now we're going to divide both sides by 100. So that's going to give us 1/10. Equals e to the negative natural log of 2 divided by 5730 t. And again, if we take the natural log of both sides, we get the natural log of 1/10 equals the natural log of e to the negative log 2 over 5730 t. And of course, the natural log is going to cancel with the natural exponential. And so what do we get? We get the natural log of 1/10 is equal to the negative natural log of 2 divided by 5730 times t. And so t is equal to what? The natural log of 1/10 times 5730 divided by the negative natural log of 2. And if you put that in your calculator, you're going to get an approximate age of what? You get an approximate age of 19,035 years. So approximately 19,000, 35 years, or approximately 19,000 years. Now here's your problem. So let's say if we have 100 grams of carbon-14, right? So let's say we have 100 grams of carbon-14. How much is left after, they don't give a date. Okay, so let's do this. How much time is left after let's do 1,000 years. So how much carbon is left after 1,000 years? If an artifact is originally contained 100 grams of carbon-14, but now contains 20 grams of carbon-14, how old is it? And again, round your answer to the nearest 100 years. That's it. Have a great day.